In the previous lesson, we have built a simple convolutional neural network for identifying handwritten digits from scratch and trained it to achieve a reasonably high accuracy of nearly 97%. However, the problem that we considered was rather simple due to a relative uniformity of digits as object categories go, the presence of a clear foreground and background, and the small image size of 28 by 28 pixels. More complex computer vision tasks require more complex CNNs, and state of the art computer vision models tend to have pretty complex architectures. Luckily, we usually do not need to build such models ourselves. For a lot of computer vision tasks, pre-trained models that perform very well are available to import and use out of the box. Many of these models were originally designed for the ImageNet Large-Scale Visual Recognition Challenge, a famous image classification and object detection competition. The ImageNet dataset that is used for this competition is maintained by Stanford University. It contains over 14 million labeled images of objects in 1,000 categories. In this lesson, we will use two CNN architectures for computer vision tasks that have won the ImageNet challenge some years ago: AlexNet, the 2012 winner, and ResNet, the 2015 winner. AlexNet, designed by the Ukrainian-Canadian computer scientist Alex Grzewski and co-workers, constituted a breakthrough in deep learning when it won the ImageNet challenge in 2012, but is a relatively simple CNN architecture by modern standards. The input images for AlexNet are rescaled to be square with dimensions of 227 by 227 pixels. The CNN itself consists of the same elements that we have used to build our CNN in the previous lesson: convolutional, max pooling, and fully connected layers. The first convolutional layer uses 96 filters, with a kernel size of 11 and a stride of 4 pixels, resulting in a 55 by 55 pixel image with 96 channels. This image is then passed to a max pooling layer with a kernel size of 3 and a stride of 2 pixels, so that when the filter is shifted, the area of the image that it covers overlaps with the area of the image that it covered in the previous step. This max pooling layer reduces the dimensions of the image to 27 by 27 pixels, still with 96 channels. The output is passed to a second convolutional layer, which uses 256 filters with a kernel size of 5, a stride of 1, and a padding of 2 pixels. This layer produces a same convolution with dimensions of 27 by 27 pixels and 256 channels. The output is then passed to a second max pooling layer with the same parameters as the first one, apart from the number of channels. This max pooling layer reduces the dimensions of the image to 13 by 13 pixels with 256 channels. It is followed by 3 convolutional layers without pooling layers between them. All 3 of these layers use filters with kernel size 3, a stride of 1, and a padding of 1 pixel, and thus produce same convolutions. The first 2 layers use 384 filters each. The third uses 256, so the dimensions of the output from this layer are 13 by 13 pixels with 256 channels. The resulting image is passed to a final max pooling layer with the same parameters as the second max pooling layer. The output of this layer has dimensions of 6 by 6 pixels with 256 channels, a total of 9,216 elements. This output is flattened and passed to the fully connected part of the CNN. The first and second fully connected layers have 4,096 output neurons each. The third fully connected layer is the output layer and has 1,000 neurons corresponding to the 1,000 classes in the ImageNet dataset. ReLU activation functions are applied for all convolutional and fully connected layers except for the output layer that uses the softmax activation function. The value for each neuron in the output layer can thus be interpreted as the probability that an image contains the object from the corresponding ImageNet class. Let's take a look at how the AlexNet model that has been pre-trained on the ImageNet dataset can be used in practice. First, we need to import and pre-process the images that we will be testing the model on. We will import a single image of a yellow lab using the Pillow library. Then we will use torch vision transforms to pre-process the image, similarly to what we have done in the previous lesson. In this case, we will first resize the image to be square with dimensions of 256 by 256 pixels, then crop out the center of the image down to dimensions of 224 by 224 pixels, thus removing the area near the boundaries of the image so that we can focus on what is at its center. We will transform the resulting image to a PyTorch tensor and normalize the pixel intensities. We can display the image after all these transformations using the mshow function that is contained in the pyplot module of the matplotlib library, not forgetting to permute the dimensions of the PyTorch tensor so that they are in the order image width, image height, color channel, the same way as we have done in the previous lesson. We ascertain ourselves that the dog is still recognizable in the transformed image. Finally, we create an image batch, in this case, one consisting of a single image that will be used as input for the pre-trained AlexNet model. Using the pre-trained AlexNet model is very easy. We can import it from torchvision.models and create an instance of the model, specifying that we want to use pre-trained weights by setting the pre-trained parameter to true. We set the model to evaluation mode using the eval method, similarly to what we have done in the previous lesson for our custom CNN. Then we run the model on our image batch. The output is a row vector with 1000 elements, each corresponding to one of the 1000 classes in the ImageNet dataset. To interpret this output, we need to download the class labels for ImageNet. We can do it using the command shown on the slide. The output of the pre-trained AlexNet model has not had the softmax activation function applied to it. We will apply this function and then print out the top 10 class labels with the highest probabilities, as determined by AlexNet, and the corresponding probabilities. The top class label for this image is Labrador Retriever, the correct one, with a probability of over 41%. The second most likely class label, with a considerably lower probability of about 16.5%, is Golden Retriever, a dog breed that is relatively similar in appearance to a yellow lab. All other class labels in the top 10 are also dog breeds. Therefore, AlexNet performs very well on this image. The 2015 ImageNet Challenge winner, ResNet, is a much larger convolutional neural network than AlexNet. ResNet type architectures come in various sizes. The one that we will consider here is ResNet 50. It is schematically shown on the slide on the left. Notice that the boxes labeled conv_block and identity_block in the schematic are not single layers, but rather blocks with relatively complex architectures that are shown in the dashed boxes to the right. Also notice that some of these blocks are repeated multiple times, as indicated by the labels ×2, ×3, and ×5 in the schematic. The ResNet 50 model architecture is therefore very complex, even though it consists of the same basic layers that we have seen in smaller models before. Luckily, running it is as simple as running AlexNet. It can also be imported from torch vision models. An instance of the model is then created, specifying that we want to use pre-trained weights by setting the pre-trained parameter to true. The model is set to evaluation mode using the eval method and is then used by passing it the image batch to be classified as output. To this day, ResNet 50 remains a sufficiently accurate model for most image classification tasks that you may encounter in practice. Let's see how it performs on the same image of a yellow lab that we used to test AlexNet. Just like for AlexNet, we apply the softmax function to the output of ResNet 50 to get the probabilities for each of the class labels in the ImageNet dataset and display the top 10 most likely class labels with the corresponding probabilities. Just like AlexNet, ResNet 50 predicts the correct class, Labrador Retriever, as the most likely class. In fact, ResNet 50 is more certain about it than AlexNet. It returns a probability of about 51.8% for this class versus about 41.6% returned by AlexNet. Just like for AlexNet, almost all other labels in the top 10 are dog breeds, albeit not always the same ones that AlexNet predicts. The one class label that is slightly unexpected is tennis ball, that appears with a probability of about 2.7%, until we realize that many of the images that were used for training ResNet 50 on this class may have been images of Labradors retrieving tennis balls. Thus, the neural network learned to expect that a presence of a Labrador correlates strongly with the presence of a tennis ball. Good guess, ResNet 50. We have seen how pre-trained models can be used for image classification. Now, let's briefly consider how they can be used for object detection. This task requires not only classifying an image as containing an object that belongs to a certain class, but also finding the bounding box around that object in the image. One way to go about solving this problem is the sliding windows detection algorithm. The basic idea behind it is that boxes of various sizes are scanned across the image. The area of the image that falls within each of these boxes is cut out, and the image that is obtained as a result is run through a classification algorithm to detect whether the object we are looking for is present in the fragment of the image that has been cut out. We won't consider the details here, but convolutional neural networks allow performing this check efficiently for all areas of the input image. Thus, they can be used to not only classify whether the image as a whole contains a given object, but also which specific part of the image contains that object. The accuracy of the bounding box for each object that is obtained by a machine learning algorithm can be quantified using intersection over union, or IOU, perhaps the most popular performance metric for object detection algorithms. To calculate the IOU, we need to take the area of the overlap of the bounding box that is predicted by the machine learning algorithm with the ground truth bounding box that has been manually drawn and divide it by the area of the union of these two boxes as illustrated on the slide. The more similar the two bounding boxes are, the closer the IOU value will be to 1, indicating good performance by the machine learning algorithm. The more dissimilar the two bounding boxes are, the closer the IOU value will be to 0. Just like with the image classification algorithms, before we can run an image through an object detection algorithm, we need to import and pre-process it. This time, we will import the image using the popular OpenCV library. We will then perform some pre-processing on the image, convert it to a PyTorch tensor, and normalize the pixel intensities to be in the range between 0 and 1. The object detection model that we will use as an example, like many other object detection models, has been pre-trained on the Common Objects in Context, or COCO dataset, a large-scale dataset that is commonly used to train algorithms for object detection, segmentation, and image captioning. This dataset is periodically modified, and the 2017 version that was used for training the object detection model we will be using has uh, 80 class labels across 12 general subcategories. We can download the annotations for this dataset in JSON format and print them out with the code on the slide. Here are the COCO dataset categories. As you can see, the dataset categories include people, certain animals, as well as an assortment of vehicles, electronics, appliances, food and household items, etc. Objects in these categories can be detected by the model that we will use here out of the box. The image that we will be testing our pre-trained image detection algorithm on shows a dog, class ID 18, in the COCO dataset, so we are good to go. The model that we will be using is RetinaNet ResNet 50 FPN, an object detection model that is based on the ResNet 50 architecture. It uses ResNet 50 as a backbone that is responsible for computing a convolutional feature map over an entire input image and combines it with two additional relatively simple subnetworks, one of which performs convolutional object classification on the backbone's output, and the other performs convolutional bounding box regression. RetinaNet is trained using a focal loss function to address class imbalance, the relative abundance of objects from certain classes in the training data and the relative rarity of objects in other classes. Focal loss is a modification of the cross entropy loss that adds a modulation term in order to focus learning on hard negative examples. The model can be imported from torchvision.models.detection. It is initialized the same way as AlexNet and ResNet 50 by creating an instance of the model class and specifying that we want to use pre-trained weights by setting the pre-trained parameter to true. When we set the model to evaluation mode and run it on the image of the yellow lab that we imported and pre-processed, the output of the model contains the category numbers in the COCO dataset for the identified objects, the bounding boxes for them, as well as the confidence levels associated with each prediction. We set random colors for bounding boxes and corresponding labels, and superimpose the bounding boxes and labels for them onto the original image, whenever the prediction confidence level exceeds 50%. This restriction is set to avoid returning multiple labels for the same object. Here is the model's output for the picture of the yellow lab. It identifies a single object of the classes known to the model in the image and determines that it is a dog with over 96% confidence. The model can also identify multiple objects in the same image, even when the objects partially obscure each other. However, it is limited to identifying objects in the 80 classes of the COCO dataset that the model has been pre-trained for. The pre-trained models for image classification and object detection are powerful and easy to use out of the box, but only work for a limited number of classes. If we need to identify other types of objects, these models need to be retrained. Given their size and the great number of parameters that they have, retraining such models from scratch would require very large datasets and would be computationally very expensive. Luckily, it can be avoided using transfer learning, a topic that we will discuss in the following lesson.